to section 8.3. I've got a very brief outline of the history of rainbows here, and I discovered some interesting things along the way as I was writing it, like vision coming from the brain, not the eyes, and the gunpowder formula. But what I'm really after is down here, the supernumerary is that double rainbow that you see sometimes, and that can be explained with Airy's equations. And those are power series solutions to a differential equation. So that's what we're going to talk about today. All right, so the method we use today is going to be valid around ordinary points. Now, ordinary points, I've got the definition here, but basically it means that P and Q are very well-behaved functions. In the last lecture notes, I have a description of analytic functions and some examples, but basically you want to avoid dividing by zero. If you don't have an ordinary point, you have a singular point, and there are methods for finding infinite series solutions around singular points as long as the singular point isn't too bad. And so we're going to be pretty much in this case just trying to avoid dividing by zero. So for example, if we're looking at this differential equation right here, in order to find the singular points, we need to get it into the form of a monic differential equation. So we need the coefficient of y double prime to be 1. So we're going to divide through by x and get y double prime minus x y prime plus 5 over x y equals 0. So my p of x is negative x. No problems there. That's fine. Q of x is 5 over x. We've got an issue there. We can't divide by 0. So we know we have one singular point at x equals 0. All right, so this theorem here says if we're working around an ordinary point, we can find two linearly independent power series solutions centered at the ordinary point. And rather than just read through that whole theorem, I'm just going to show you how it works with Airy's equation. So here we've got a differential equation. X equals 0 is an ordinary point, and so we can find power series solutions around that point. So we're going to start by assuming y is the sum n equals 0 to infinity of Cn x to the n. That will always be our start if we're centered at 0. So y prime will be the sum n equals 1 to infinity n Cn x to the n minus 1. And y double prime will start at 2. N equals 2 to infinity n minus 1 Cn x to the n minus 2. Okay, now we plug in, and we're plugging in to the differential equation up here. So we get y double prime, which is the sum, n equals 2 to infinity n minus 1 Cn x to the n minus 2 plus x times y, which is the sum n equals 0 to infinity of Cn x to the n. And it's important that you set that equal to 0. This is an equation. All right, distribute. So what I mean here is in this case, we need to distribute this x. So the first power series, I'm not going to do anything to, n minus 1 Cn x to the n minus 2 plus, now I get the sum n equals 0 to infinity Cn, and I'll have x to the n plus 1. All right, reindex. I want to reindex. So everything is expressed in x to the n. So for this first power series, I need to add 2. So that means down here at the base, I'm going to subtract 2, and I'll start at 0. And then I'll have n plus 2, n plus 1, Cn plus 2, x to the n. And then the next one, I need to subtract 1 up here. So at the base here, I'm going to add 1, start at 1 to infinity Cn minus 1, x to the n, and that equals 0. Okay, and then cull and combine. So in the last lecture notes, I culled separately and then I combined, but I think you can all do this pretty much in your head. We need to take out the 0 term from this guy, so it starts at 1, and then we can add. So if I take out the 0 term, I get 2 C2, and now they both start at 1, so I'm just going to combine them, n equals 1 to infinity, big bracket, n plus 2 n plus 1, Cn plus 2, you can see why we did all this practice in the previous lectures, plus Cn minus 1, close bracket, x to the n equals 0. Okay, now the fun part starts. We set all the coefficients equal to 0. So the constant coefficient is 2c2. So 2c2 equals 0, so I know now that c2 is 0. Then I set this coefficient equal to 0, and that's what I did right here. And typically that will involve two c's, and you're going to solve for the larger index. So I'm solving for cn plus 2 in terms of cn minus 1. And then you write down what n that's valid for. So that's going to be valid for wherever your infinite series starts. In this case, it starts at 1. And that's my recurrence relation. So I've got those little hints right here. Now we just start plugging in. When n is 1, so I'm going to plug into this formula. When n is 1, I get C3 equals negative 1 over 6 C naught. Okay? And then I did the rest for us because I don't think you want to sit here and watch me do arithmetic, but let me just go through a couple of things. When n is 2, I get C4 in terms of C1. Everything's going to have to be written in terms of C0 and C1. So for n equals 3, notice, I get C5 in terms of C2, but I know C2 is 0. So in the beginning, I was asked to find all terms up to degree 5. So that would mean I only need to go up to C5, and I could technically stop here, but I got a little overexcited and I went up here and I found C6. You can see C6 is in terms of C3, but I know C3 is in terms of C0, so I was able to write C6 in terms of C0. And you just keep going until you get to the C that you want. All right, so now the step that's important is this step, and it doesn't seem important because it's just writing down the generic formula for y. It's what we were assuming to begin with. Y is C0, C1x, C2x squared. But students that get this step wrong, step 7, are usually the students that don't bother with step 6. So step 6 can really help you because you just read off of this, but you replace the C's with what you know. So we know C0 is C0. We don't know anything about that. C1 is C1. All right, but C2 we do know something about. C2 is 0. So 0 goes with x squared. And then C3, looking up here, is negative 1/6 C0, and that gets paired with x cubed. And then C4 is negative 1/12 C1, and that gets paired with x to the 4th. And then where are we? C5 is 0. So I could stop there, and we want terms up to degree 5, but I'll just add the last one on since I did it. 1 over 180 C0 x to the 6th, dot, dot, dot. Okay, then you're going to write down all the C0 terms. So I factored out a C0, and I'm going to write down the terms that get paired with C0. So a 1, and then minus 1/6 x cubed, and then plus 1 over 180 x to the 6th. And then I write dot, 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 but in your homework, I have an example here of how you're going to format your homework. You're not going to put the dot, dot, dot in the parentheses because they put the dot, dot, dot after the parentheses for you. All right, and then our C1 terms are x minus 1/12 x to the 4th, and that's all I have for my C1 terms. And again, if you were doing this for a homework problem for your C0, you'd stop here because you don't want the term of degree 6 if they're only asking for terms up to degree 5. Okay, let's do one more. This time we're going to solve an IVP, but we're not going to worry about the IVP part till the very end. So we're going to start, they all start with sum n equals 0 to infinity Cn x to the n, that's y, and then y prime starts at 1, n Cn x to the n minus 1, and y double prime starts at 2, n minus 1, Cn x to the n minus 2. Now we plug in. So we're plugging into this differential equation. Y double prime, sum, n equals 2 to infinity, n minus 1, cn x to the n minus 2. And then I'll have minus 2x times y prime, which is 1 to infinity, n cn x to the n minus 1. And then plus 8y, which is sum n equals 0 to infinity of cn x to the n. That equals 0. Don't forget your equals 0. Distribute. Okay, so I need to distribute the negative 2x and the 8. So the first power series doesn't change. 2 to infinity, n minus 1, cn x to the n minus 2. Then minus twice, n equals 1 to infinity, twice n cn, and now it's just x to the n because I add the exponents, and then bring the 8 in, n equals 0 to infinity, 8 cn x to the n, and that equals 0. Okay, reindex. So the only one we have to reindex is the first one. So that's going to now start, this is a minus 2, so I need to add 2, so I subtract 2 down here. So this will start at 0, and it'll be n plus 2, n plus 1, cn plus 2, x to the n, and then the other two power series don't change. Okay, now we can cull and combine at once. We see this guy starts at 1, so we need to start them all at 1. That means I need to take the 0 term out of the first and last power series. So if I take the 0 term out of the first guy, I get 2c2. And if I take the 0 term out of the last guy, I get 8c0. So that's my constant term. And then I get plus sum n equals 1 to infinity, big old bracket, and I'm going to combine. So I've got n plus 2, n plus 1, cn plus 2, and then, let's see, I'm going to write this as plus 8 minus 2n cn, and then close bracket, x to the n equals 0. Let me show you what I did here. Over here, I had a negative 2n cn, and here I had a plus 8 cn. So I wrote that as 8 minus 2n cn. So that's where I got that guy. Okay, now we set all coefficients equal to 0. So this guy I said equal to 0. I did that here. So solve for C2. I get C2 is negative 4C0. And then I set this whole thing equal to 0. That's what I did here. And I solved for the larger Cn. So I solved for Cn plus 2 in terms of Cn. And just make sure you understand what I did there. I had an 8 minus 2n, but over here it switches to 2n minus 8. And that's because I was subtracting. So you might want to pause the video and just check the math on that. And that's valid for n equal 1, 2, ... So I want terms up to degree, I believe 5. So I need to go up to C5. So when n equals 1, in this formula, I get C3 equals negative 6 over 6 C1, which is negative C1. And then I went ahead just to save you the arithmetic, and I found C4 in terms of C2, but I know C2 is negative 4 C0, so I was able to write C4 in terms of C0, and I was able to write C5 in terms of C1. Everything has to be in terms of C0 and C1. Okay, then we plug in. And again, don't skip this step. Just write down the generic formula for y, and now we're going to plug in. So we got y equals C0 plus C1x, and then C2 was negative 4 C0, and that gets paired with x squared. And then C3 was negative C1, and that gets paired with x cubed. And C4 was 4/3 C0 x to the 4th, and then C5 was 1/10 C1, and that gets paired with x to the 5th, dot, dot, dot. All right, and so then we write this as C0, and the C0 terms are 1 minus 4x squared plus 4/3 x to the 4th, dot, 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 and then plus C1. My C1 terms are x minus x cubed plus 1/10 x to the 5th, dot, dot, dot. Again, you're not going to put the dot, dot, dot when you do your homework. All right, so if we were just finding a general solution, we would be done at this point. However, this problem wants you to solve the IVP. And so what I've done, you only have one homework problem where you do have to solve an IVP, and I've written down the solution. It's fairly straightforward. You just solve it like you would solve any other IVP. The only twist is it's on step 2, you're going to have to find y prime, and the way you're going to do that is just take the derivative of y term by term. So there's nothing too tricky going on there, and I trust you to read that on your own. Okay, and that is the end of this section.